Hello everyone, welcome to APC Mechanics 2019, Set 1, Question 2. So as you see here in the question, it's kind of a classic APC problem. Multiple topics, you've got a pendulum swinging, you've got it running into another block, so there's a collision, and then the other block becomes a projectile, and the first block keeps swinging. Couple of things to pick up here in the original diagram as well as in the statement. The block attached to the string has a mass of 3m, whereas the block sitting on the table has a mass only of m. Right? The length of the string here is L, the height of the table is 2L, and the block lands a distance 4L away from the table. Eventually this thing swings out to an angle we'll call theta max. And if you read through the problem statement, key thing here, air resistance and friction are negligible. Right, so this will be a projectile motion problem eventually. And all answers must be in terms of m, L, and physical constants, a fancy way of saying little g, as appropriate. Right? Only use their variables. So, first part of the question, quick one-pointer. What's the speed of block 1 when it gets to here? Right, so just before it makes contact with block 2. So when we're dealing with swings, right, the obvious place to go is a conservation of energy problem. If the string, the block, the table, the earth, everything basically is in the system, then energy is conserved. Initially, all of the energy is gravitational potential up here, and finally, all of the energy will be kinetic if we call this our zero of Eg to make life convenient. So as you can see down here, they jumped right to that. Right, those two are equal. You get your classic mgh and your 1/2 m of v squared. H, of course, is L. Right, this is the distance that it's fallen. Right, and notice that the m's cancel. Technically, a little sloppy, I think, on their part. This is actually 3 capital M and 3 capital M, but they're going to cancel out anyway, right? Since it's this block, right, which is 3m big. Do all the math, and there is your answer. Square root of 2gl. Right? Note, little interesting thing in the rubric here, even if you show no work, if you just write that, because you've done this problem many times, and you have, right, you can get the full credit because it was only a 1-point problem. So a little interesting one, they don't always ask this. They want you to draw a force diagram when block 1 is here just before it makes contact with 2. Note that it is fully vertical at that point. Okay? And another little interesting thing about this force diagram is that it doesn't just want you to list and label the forces. It also wants you to draw them size-wise, right, compared to what they'd actually be in real life, which is, of course, something we always do with our force diagram, but the AP does not. So, at this point, you've basically got 2 forces. You've got gravity acting down. They call that F of W for some reason. Okay, whatever. Could be capital W, could be F of G. They'd accept any of those. And you have the force of tension in the string acting upward, which they call F of T. Moving towards our symbols, sometimes they call that a capital T. So you draw those 2 forces, that's a point. Now the question is, how big are those forces? And your tendency might be to say, oh, well, it's on a horizontal table or it's just above a horizontal table. Therefore, everything is equal and balanced. But this block is moving in a circle. And since it is moving in a circle, it is constantly changing direction and therefore is accelerating. Right? It's also changing speed. Right? And so, at that point, the acceleration is radial, right? Which means inward, which means upward. Right? This is basically a centripetal force kind of situation. And for the net force to be upward, F of T must be larger than F of W. There's your second point. Okay. Now that, of course, is going to come in later when we do a force analysis at that point, as you might imagine. So important that you don't draw these as the same size, which would mean it wasn't accelerating, which it is, because it's moving in a circle and changing its speed. So now so there you go, right? Part C. Did I miss a part? Let's go back. Oh, no, I didn't. Here we go. Part C, they want you to find the tension in the string. So we have the force diagram here already. right? F of t and F of w. So we're going to apply Newton's second law. Right? Newton's second law says net force is mass times acceleration. Now, they didn't write the steps out here. I would have appreciated a step or two more. So if this was me, I would write this as F of t minus F of g, because F of t is up and F of g is down, equals ma, and since the acceleration is inward or upward, it would also be positive. So I would get F of t minus F of g equals ma. And then if you solve for F of t, you get this. And note, it's not just any acceleration, it's the centripetal acceleration, right? Because the net force is acting inward or radial in rotational terms. Right? So we know the centripetal acceleration can be given in linear terms as speed squared over the radius. Hence their substitution. Plug in everything, be careful. The m's here are block 1s, which are 3 m's. G stays as g, and v is not an allowable variable, but you know it from previous, right, as the square root of 2gl. And then if you simplify, you get 9mg. Kind of surprised this isn't a 3-point problem where they give you a point for substituting this in. In this case, they just basically assumed you knew how to do it to get to here. Note the key is that it is accelerating, but it's a special centripetal acceleration because it is inward directed. Part D. So now they want you to calculate the time between the instant block 2 leaves the table and the instant it first contacts the floor. Sounds like a projectile problem, and indeed it is. And with almost all projectile problems, when finding the time of flight, we tend to use the third kinematic equation. Right? Here they wrote it out this way. Note, if you go back to the diagram here, it's coming off the table horizontally. Hence, the initial vertical velocity is 0. Right, so that drops away. Of course, our acceleration would be little g. Right? And if you solve for time, you get this. And if you plug the numbers in, you get that. Although, be careful. The table here is 2L off the ground, right? Not just L. And notice up here, they told you what L was. But you have to convert to meters, right? Because little g is in meters per second squared. Now you want the speed of block 2 as it leaves the table. Well, again, it's horizontal, so that would be Vx. And so horizontally, the speed of a projectile is constant. So we use the constant velocity equation. Horizontal displacement, otherwise known as range, is Vx times t. Solve for Vx. Again, be careful. The range is 4L if we go back to the original picture. Right, range is 4L given to you in the problem. Right, so you get this, and if you plug the numbers in, you get 5.45 meters per second. Note here, they did give you a point for substituting what you found in Part D into the equation. And they would probably give you full credit here if you somehow made a mistake here, like, I don't know, you forgot to square root or something. They would give you the full credit down here as long as you plugged in what you found in D properly into E. Now they want to know the speed of block 1 just after it collides with block 2. Well, we're talking about a collision here, right? A collision. And hopefully, when you see a collision, you think momentum conservation. Right? So if you include the two blocks, right, that it's a closed, isolated system, none of the mass leaves, and the forces are between the blocks, and therefore, momentum is conserved. So here they wrote the initial momentum is equal to the final momentum. Right? The momentums are vector sums. Right? You're adding up the vector quantities. They don't use arrows on these keys, unfortunately, but technically these velocities are arrows. Right? And so the two initial momentums are equal to the two final momentums. Of course, the initial momentum of the second block is 0 because it wasn't moving initially. Again, you have to be careful with the masses. Remember, block 1 is 3m, block 2 is just m. So if we solve for V1F, sorry, right, and then we plug in all the numbers. Now, they plugged in square root of 2GL here from part A, I believe. You also could just plug in the number, of course, and you would get the right answer since they want a numerical answer. right? And it's about 2.02 meters per second. I'm sure they would accept 2.0 there, right? You might get 2.1 if you're using 10 instead of 9.8, but it's all good. They would know that. So again, key here is that you're analyzing a collision to kind of work backwards, right? And, to see what block 1 is doing after the collision. And collisions are usually analyzed with momentum. By the way, you can't use those big, fancy, elastic collision equations that we derived in class because there's no reason to expect that this is an elastic collision where kinetic energy is conserved. Right? It doesn't say that it is, doesn't give you any evidence that it is, never assume that it is, all right, unless they tell you. So, last part, which is kind of the big part, the hardest part, I think, of this, is you want to calculate the angle theta max. Again, if we go back to the original diagram, say that's the angle that block 1 goes out to before it stops. So, swings again, kind of like the first swing. We're going to do a kinetic energy conservation of energy problem if we put the block and the Earth into the system. It's kind of backwards from part A because in this case, the block starts out as all kinetic if we call that bottom height our 0 of Eg and ends up at the end as all Eg. Right, so we plug the 1/2 mv squared in and the mgh. Now, here's where you got to be a little careful. What is h? H is the height that it moves through as it swings. So over here I've drawn a little diagram to help us see. All right, so here is L. Right, this has a length of L. This is where the block starts. And here is L at theta max. So these are both L's. If I drop a little horizontal in here, hopefully you can see that this part is L cosine theta. It's the adjacent side, right? Since this entire length of the string is L, then this little part is L minus L cosine theta, and that's actually your height, or what we would call yi, right? What they call h. That's how much the height changes in the box swinging from here to here. So take a second and check that over, hit pause, whatever, and make sure that you understand this. This is a very common kind of APC thing for them to do. I think on our actual energy test, you had to do it on a multiple choice question, but on swinging things, it's pretty common to look at this L minus L cosine theta thing for height. Here they write that out here. Notice that's a point if you get that. All right, so as long as you do conservation of energy, you get 1 point. If you plug in the right yi, you get a second point. And then if you plug everything in that you knew before, right, and solve, right, you get down to about here. Notice their use of the 2gl for square root of 2gl, which gets squared for the speed. Right, so they're working symbolically. And then you have to take an inverse cosine, right, once you solve for cosine of theta. So you'd have to move this over there, and this would be 1 minus this, right? That's how they get this. You do the math. Inverse cosine, make sure that you are in degrees, make sure that you're using parentheses or that you're determining what this is before you plug it in. Right? Notice that this is g, but it's not a vector g, it's not a negative. Right? This is not a kinematic equation problem, this is an energy problem where we work with scalars. And you end up with about 43.5 degrees, which is what that is in my diagram. And they would take a 44 if you're using 10.